So we have talked about the functional linear models. So now let's start a new topic. So as we mentioned in the beginning, that one advantage of functional data is that we look at the function change over time, right? So when we look at a function, then we are able to look at the derivative, the function, which represents the rate of change of the function. And we can also look at the second derivative of the function, which represents the acceleration of the change, right? So so if we are looking at the derivative, then there's many things we can do. So in fact, there's a big areas to model the derivative of the functions. So one central models to model the derivatives is the differential equations. Okay. So how many of you have learned differential equations before? Can you raise your hand if you learned differential equations? Okay. So when we are working on the smoothing splines, we have talk about we can define the roughening penalty using the differential equations, differential operator, right? So today we will going to look at a new topic in functional data analysis, which is how can we using the functional data to estimate the dynamic model on the functional data, which is estimating the parameters in the different equations. Okay, so let me first give you an introduction about these problems. So here is a general form of ordinary differential equations. So basically, we have this is the equation, right? On the left side, we have the derivative of the x feedback to t, and on the right side is the g function. The function g function is the function of x. Okay. Suppose we have a function x of t. Okay, this function can be multivariate. So I'm using the boldface here, bold font here. So we can see here we have this beta, which is the parameters. We don't know. We call OD parameters here, and so you can see the different equations kind of to link the derivative of the function to the function itself, right? So in other words, the derivative represents the rate of change of this process, right? So the rate of change of the process will depend on the current state, right? So for example, this is when you drive the car, right? So when you drive the car, if you think your car is going too slow, you may your velocity. Suppose this x is the velocity of the car, right? So when you think your car is driving too slow, the velocity x is small, then you may want to accelerate, right? Accelerate your car. So in that case, you may give a positive derivative on the velocity to increase the velocity of the car. And if your car is going too fast, the speed of the car going too fast, you may try to slow down the car, right? So you want to take the derivative to be negative and to lower the speed of the car, right? So this actually is very natural when you want to model a dynamic process. So the rate of change of this process will depend on the current state of the process. Okay, so this is the ordinary differential equations. So actually, because of this ODE are able to model the rate of change of the process, many fields using differential equations for their models. For example, in the engineering, physics, biology, many fields are using differential equation to model their dynamic process. For example, the famous Newton's second law, which is the force F equal to the mass m times the acceleration, which is the second derivative of the position functions. So this is actually can also be looked at as the ordinary differential equations. So in general, for the differential equation, they can provide very simple models for very complex behavior. Therefore, it's very popular to model the dynamic process. So the challenging part for the ordinary differential equations compared to the regular linear regression models is that most ODEs do not have analytic solution. Therefore, we can only obtain the solution of the ODE based on some numerical methods. So basically, these numerical methods are able to find the ODE solutions given the ODE parameters and initial values. And these ODE solutions are very sensitive to the parameters and initial values. A very small change on the initial values, it can have a big change on the solution. Okay, so this is one thing we have to be careful when we're using the ODEs. So, in applied mathematics, there's many research try to study how to get an accurate numerical math solution on the differential equations. So this is not the topic for statisticians. So we are kind of working on the inverse problem. So why is called inverse problems? So, so the original problem is to giving ODE parameter beta to find the solution, right? So now we are going to the inverse way. The inverse way is that suppose that we have some observations on the solution x of t, and we want to infer the ODE parameter beta. Okay, therefore this is called inverse problems. Okay, so there's actually a very big areas on these inverse problems on how to estimate the ODE parameters based on the observations. Okay. So let me give you one applications in biology, just so you get the ideas how this problem looks like. So here, this is a predator-prey system designed in a biology lab. Okay, so basically in the lab, we have a big water tank. Okay, so in the tank, there's inside the tank, there's two species. One is called rotifer, which is a predator here, and the other is the algae, and this is the prey. So the rotifer eat the algae. Okay, and there's also the nitrogen constantly flow into the system, and this system to keep it constant, it can be removed at a certain rate to make the volume of the water in the same levels. Okay, so here this is a predator-prey systems. So in this system, they are able to measure the population of the rotifer and algae, and they can see how this dynamic change between this rotifer and algae. So this is based on this system, Fussman and his co-authors published a model, an ordinary differential equation model in Science for this system. So basically, in their ODE models, they have 4 variables, the N, C, R, and B. Okay, so N here represents the concentration of the nitrogen, and which is the nutrition for this system. And so algae is the growth of algae depends on the concentration of the nitrogen. Okay, C is the concentration of algae, and R is the concentration of the rotifer with the reproducing ability, we call it female rotifer here, and B is a concentration of the total population of the rotifer. So here they have these 4 differential equation models. Okay, so actually these differential equation models looks complicated, but actually it's very easy to come up or interpret. For example, here let's see. So let's look at the last equation to give you one examples. So here this total rotifer, the rate of change of the total rotifers will depend on the population of the female rotifers, right? It's positive depend on this because more female rotifers is easier to reproduce the new rotifers, right? And so here this FBC in front of R represents the reproducing rate of the rotifer, right? And so you can see here this reproducing rate will depend on the C. The reason is because it's more algae there. It's easier for the rotifer to get the food, and then it's easier to get to have a higher reproducing rate, right? Okay, and the second term, which is a negative term. Okay, so here there's a 2 rates here multiplied by B. So this M here represents the mortality of the rotifer, okay, like the death rate of the rotifer, okay, and this delta represent remember in the system the system is removed at a constant rate delta, right? Okay, so therefore we have this delta plus M, right? So you can see it's very easy to interpret these models. So the change of the B will depend on the female rotifer positive term and also negatively related to the population of the rotifer with the mortality rate M and the remove rate delta, right? And so let me see. Let's look at this C here. So the second term here. So the second term here, this is the rate of change of the algae, right? And so you can see here the rate of change of algae will proportional to the C. This is easy to understand because the more algae it has, the easier it will reproduce in itself, right? And also this term here in front of C represents the growth rate of the algae. And this growth rate of algae will be a function of nitrogen. The reason is because the more nitrogen it has, the more nutrition for the algae, it will grow faster, right? This is easy to understand. And the second term is a negative term. So this negative term is basically the linear function of the B, is the rotifer. So the rotifer will eat the algae, right? So the more rotifer, the easier the rotifer, the algae will decreasing, right? Therefore, it has a negative term, okay? And so here, so there's a term FBC in front of B represents how fast the rotifer will eat the algae, right? And so this eating rate will depend on the concentration of the algae. The reason if you have more algae around, it's easier for the rotifer to eat, right? This is easy to understand. And here, this epsilon will represent the consumption rate. Okay, so suppose there's algae everywhere, there's still a rate for the rotifer to consume itself, right? Okay, and also there's a negative term minus delta C because the system is removed from the tank at the rate delta, right? So all the components inside the tank will remove at the rate delta. Okay, so this is easy to understand, right? So for the first equation, the left side is the rate of change of the nitrogen inside the tank, And you can see here we have a positive term is this delta N star, which is represent the nitrogen is going inside the tank at the rate delta, right? And then there has a minus delta N, representing the nitrogen is removed from the system at the rate delta, right? And then it will have another negative term, which represents the nitrogen is decreasing, right? Because the algae will consume the nitrogen, right? So therefore, this have this negative term, and the rate will depend on the function of nitrogen, because the more nitrogen, the easier for the algae to consume the nitrogen, right? Therefore, it has a negative term. Okay, so for the third equations, this is to model the rate of change of the female rotifers. You can see here, firstly, the change will linearly depend on the number of female rotifers. The reason is because the female rotifer will reproduce in the new female rotifers, right? And the second term is a negative term. We also depend on the linear depend on the rotifers, female rotifers. The first, the delta is the rate every component will remove from the tank at the rate of delta, right? And M is the death rate of the female rotifers. That's for all the rotifers, they will die at a certain rate. And there's another term called alpha. So this alpha represents the female rotifers after a certain age. It will not lose the reproducibility, right? This is also easy to understand, right? Yes, therefore it has this alpha. The alpha represents the rate of the female rotifer losing their reproducibilities. Okay. So this is easy to understand, right? So you can see here for these four equations, this model, these four components inside these predator pre-systems, but all these equations, it has a very easy interpretations, right? Okay, so therefore, it's very easy to understand, and also more importantly, you can see for these equations, it is are able to so here the circles represent the observed concentration of the algae and the rotifers. Okay, and the dashed lines is the solution of the ODEs. And you can see here for a nice thing about this predator prey system. Predator prey system is a very popular ecology system. The reason is that you can see a very nice cycles of these two populations. For example, you can see here this the concentration of the algae will firstly increasing, right, and then will decreasing. The reason is decreasing because when the concentration of algae increases, then it will produce more nutrition on the rotifers. So the rotifer population will keep increasing, right? When the population of the rotifers increasing too much, then they consume too many algae. The algae will become decreasing, right? And then the rotifer will keep reproducing new rotifers with enough nutrition. But after a certain peak at this time, then it will decrease. The reason because there's too little algae left, so that it doesn't have enough nutrition. So therefore, the population of the predator will decreasing now, right? And then it will decreasing to a certain time. Then the algae will able to grow faster, increasing because there's less predator there, right? This kind of cycles can be found in many ecology systems, right? Yeah. So you can see here the dashed line is the solution, numerical solution of the ODE. You can see this solution are able to producing this cycle behavior of this process, right? So that's why their ODE system for such a simple ODEs, it's able to reproduce in this periodic behavior of this predator-prey system. Therefore, it's very interesting. It can be published at the Science. However, if we will, we talk a lot in this course about fitting the data, right? And if you look at these ODE solutions, you can see that although this solution mimic the periodic behavior of this predator-prey system, if you look at it closely, the data actually is far away from the solution, right? It's not close at all. Especially if you look at it like this part, right? And this part is not close enough to the data, right? So ideally, when we model the system, especially in statistics, we certainly want the model able to fit the data, right? We don't want to be the model to be far away from the data. So therefore, this model is not 100% satisfactory because it's not close to the data. The reason it's not close to the data is because that in these ODE systems, actually there's many parameters. For example, M represents the mortality rate of the rotifer, and alpha represents the decay rate of the rotifer when they lose the reproducibilities. And this epsilon represents the consumption rate of the rotifer to eat the algae, right? And so all these parameters actually cannot be observed. It cannot be measured either, okay? Therefore, how can come up with this value for these parameters will be very important, because we know that in order to solve the ODEs, we have to know the value for these parameters. So, so how can we come with the value for these parameters? A common practice in biology is that okay, so this M represents the death rate of the rotifers. So maybe they can find the literature, search on the literature to find the death rate of the rotifers. And maybe this alpha represented the decay rate of the female rotifers losing their reproducibilities. We can look at literature to find our values. However, firstly, it may be hard to find these values in the literature, right? Secondly, the find values may not be valid for their system, right? As I said, this system is specifically designed in this lab to model these predator-prey systems. So because of the condition on the laboratory, maybe there's different mortality rate for rotifers, right? So in other words, we may be able to estimate the value for these parameters to improve the fit of the model to the data, right? So the goal here is that we want to estimate the value for these parameters such that the model solution can fit the data. So, so here, these first rows represent the value given in the Fussman paper for these 4 parameters in the ODE. And so the second rows represent the value for these 4 parameters when we're using our new method to do the estimation. So, so the last row represents how close the ODE solution to the data, the mean square errors, the fit. Okay, so you can see here using Fussman parameters, the mean square error to the data is 1.96, and if you're using our new estimated parameters, the mean square error is only 0.34. Okay, so the fit is much better. So if you look at the graph, you can see here the solid line here represents the ODE solution with our estimated ODE parameters. Okay, and you can see here with our new estimated parameter values, the ODE solution, the solid lines actually are able to fit the data much better, right? Okay, so this is very good. This is a very good way to validate the models, because this model now are able to fit the data, so we can see, okay, this may be a valid model for the system. Okay. Yeah. So therefore, so this is one example. Like if we can using our statistical methods to estimate the parameters, actually we can improve the fit dramatically. Another thing I didn't mention before is that we mentioned here there's some functions like this FCN. This represents the growth rate of the algae, right? We know that the growth rate of the algae will depend on the concentration of nitrogen, right? And it should be linearly increasing with the nitrogen, because the more nitrogen, the algae will have more nutrition, algae will grow faster, right? So we know that this f function of n should be a linear function of n, right? Linear increasing function with n. So to make it to be linear, a natural way to do is to put this f of n as this form. Okay, so this is commonly used in mathematical biology to model this nonlinear rate. And so you can see here, actually this function, at least the form of this function is increased function of n, but the form actually is pretty arbitrary, right? It's arbitrarily given. It's at the linear increasing function at the increasing function of n. Same thing with the c, the growth rate of the rotifer. This is also should be this should be c here. Should be increasing with the c. However, so they give this form, but this form may not be valid, right? So one thing we can do in statistics is that we should be able to estimate this function as a function of c, and also we should be able to estimate this fc function as a linear function of n, right? If you can estimate these two functions from the data directly, then this is a good way to validate whether this functional response is good or not. So as we learned in this course that when we estimate a function, we can always estimate this function as a linear combination of the basic functions, right? Okay. So here these phi are the basic functions, and this c are the coefficients to the basic functions. So here the dashed lines is the original functional response is these functions, okay, these two functions, and the solid lines is our estimated non-parametric functions. You can see it's very close actually, right? So this is kind of a good way to validate that this functional response actually are good, right? Okay. So this is one thing. The second thing is that we can even push further. So you can see here this dashed lines is the OD solution with our estimated parameters, and you can see it's pretty close to the data, right? However, if you look at it closely, there's one point. This is point with the circles. Actually, the far away from the solution, right? Only this one. The other looks pretty good, right? And this circles is far away from our OD solution. So if you think about when we do the estimation on the parameters, this point must have a very large influence on the estimation, right? Because maybe this point maybe it's outlier, right? Yes, maybe it has too much errors, too many errors in these single observations, right? So then, how can we come with a method that are robust to these outliers? Is also a good statistical method, right? Okay, so this problem. A challenge for this application. Another challenge for this application is that you can see here in the ODE solutions, it has four components, four variables: N, C, R, and B, right? But in the laboratory, it can only observe the two variables, C and B. Okay, this is very common in the real applications. So only like 13 variables can able to observe or measure to have the data. So this N and R we don't know, are completely missing, right? So how to handle these missing variables is definitely a challenging problem, right? Yeah, the second problem we just mentioned that we have to estimate the functional parameters, the two rate function of N and function of C, and data may have outliers, right? Okay, so this is for these first applications. Let me show you another applications in genetics. So, in genetics, so for each species, there can be many genes, right? But the genes, actually, some genes they call the regulators. Okay, so some genes can regulate the expression of other genes. Okay, so then we can come with one regulation network. Okay, so here, so these arrows represent these genes is regulated the expression of these genes. Okay, so all these genes together will be compose a network. Okay, based on their regulation relationship. So if there's if one gene is regulated the other genes, there will be one connections. Okay, so the current most methods they are using is just based on the correlation of this expression of two genes. Okay, so if the expression of two genes are correlated, okay, then you will see, okay, there may be some relationship between these two genes, right? This is okay. This is how they come with this complicated network, okay? But when you just look at the correlation of two genes, there's two problems. The first problem is that you may know that these two genes are correlated, they have relationship, but you don't know the direction. Which is these genes regulate these genes or these genes to regulate these genes? You don't know the direction of this regulation, right? Okay, this is the first thing we don't know. The second thing we don't know is that we don't know the regulation mechanism. So how fast this gene to regulate the other genes, right? How so exactly the regulation, how the regulation function looks like behind this regulation network. So these are all unknown, right? So therefore, there's a need to come up with some mechanical models for this regulation network. So to understand these regulation networks, we started with the simplest network. This is a network of 3 genes. Okay, so we have found that the network, although the network is complicated, but there's some regulation patterns occurred more often than by chance. This is called network motifs. So one popular network motif is called a feed-forward loop. Okay, so basically this feed-forward loop are a special network with the 3 genes. So gene X, Y, and Z. So gene X will regulate the gene Y and gene Z, and gene Y will only regulate the gene Z. Okay, and at the same time, all these 3 genes will doing the self-regulations to themselves. Okay, so this is called a feed-forward loop. So for this simple gene regulation network, we are able to come with 1 different equations to model this regulation process. So here, y of t represents the expression of the gene Y, and z of t represents the expression of gene Z. So you can see here, on the left side is the rate of change of this gene expression. So the rate of change of this gene expression will negatively correlated with the gene expression of Y itself. This is common in biology. Like generally, when they do the self-regulation, they will depress the expression of themselves. Okay, they try to push them to be not expressed because the expression costs the energy, right? Yes. Okay, so that's they have a negative correlation. So this alpha Y represents the self-regulation rate, self-repression rate, right? And this X represents the regulation function of X, the gene X, on the gene Y. Okay, and so this regulation function can be an activation, which is an increasing function of X, or can be a repression, which is the decreasing function of X. Okay, we call the activator and a repressor. Okay, and this beta will represent this regulation rate. Okay, similarly, for the gene Z, it has this self-regulation, this negative term, and alpha Z is a self-repression rate. And the gene X and gene Y regulate Z at the same time. Therefore, we'll have this regulation function of X multiplied by the regulation function of Y. And this beta Z represents the regulation of X and Y together on the Z. Okay, so you can see here, this is a very simple differential equations. Using these differential equations, we are able to describe this regulation process very accurately, right? Okay, here for this differential equation, we have 7 parameters to estimate, and all these parameters have this biological meaning on this system. Okay, so let's stop here, and on Wednesday we will continue. Okay.